Hello everybody, and welcome to this course. This is a crash course on complex numbers. The topics that this course covers are the definition of the number I, the definition of a complex number, the definition of the complex plane, how to calculate addition and subtraction of complex numbers, how to calculate the multiplication of complex numbers, the representation of complex numbers in their polar form, how to calculate the reciprocals of complex numbers, how to calculate the conjugate of complex numbers, how to calculate the division of complex numbers, the representation of complex numbers in their exponential form, and how to calculate the powers and the roots of complex numbers. Complex numbers were invented, or we could say, discovered, to calculate the square root of negative numbers. As you may already know, if we have a real negative number, a, its square root is not in the set of real numbers. Or, to say it more simply, as long as we are in the set of real numbers, we cannot calculate the square root of a. So, the number I was introduced. I is called the imaginary unit and it is defined as the square root of -1. So, what is a complex number? A complex number can be simply represented as the sum of two real numbers, where one of those numbers is multiplied by the imaginary unit. In the example shown here, x and y are two real numbers and z is a complex number expressed as x plus yi. Z belongs to C, which is the set of complex numbers, or the complex plane. The representation of Z you saw in this example is called the algebraic form of a complex number. You will see later that a complex has two other representations, which are the polar form and the exponential form. In this section we will talk about the complex plane. As we saw in the previous section, C is the set of complex numbers, which is also called the complex plane. To visualize the complex plane, let's consider a generic complex number z equal to x plus yi. The complex number z is composed by a real part and an imaginary part. The real part is the term which is not multiplied by I, which is x in this case, and the imaginary part is the term which is multiplied by I, which in our case is y. To represent the complex plane, you can think of it as an equivalent to the Cartesian plane, where the horizontal axis is the real axis and the vertical axis is the imaginary axis. So, our complex number z will have coordinates x and y on the complex plane, as you can see in the figure on the left. In this section we will see how to perform addition and subtraction with complex numbers. Let's start by calculating the addition of two complex numbers in their algebraic form. Let's consider two complex numbers, x and y, expressed as a plus bi and c plus di respectively. We will calculate the number z, which is the sum of x and y. To perform this operation, we will simply calculate the algebraic summation of the terms of the two complex numbers, as we would do with the sum of two binomials. The number you will end up with has a real part equal to a plus c, and an imaginary part equal to b plus d. If you represent the addition of two complex numbers graphically on the complex plane, you will notice that addition corresponds to applying the parallelogram rule with vectors. Let's consider again our complex numbers x, y and z, where z is the sum of x and y. If you represent those numbers as vectors on the complex plane, you'll see that the vector z is the diagonal of the parallelogram built with the vectors x and y, as you see in the figure on the right. The vectorial representation of the number x, for example, which is a plus bi, is a vector with coordinates a and b. And if you want to calculate the absolute value of that complex number, you will see that it corresponds to the modulus of the vector which represents that complex number, which is the square root of a squared plus b squared. There is an important rule related to addition and the absolute value of complex numbers. That rule is the triangle inequality. Let's consider two complex numbers, x and y. The triangle inequality states that the absolute value of x plus y is less than or equal to the sum of the absolute value of x and the absolute value of y. To understand why this is true, let's apply again the parallelogram rule to the addition of two complex numbers. As you can see in the figure on the left, if x is the red vector and y is the blue vector, the yellow vector is the one corresponding to x plus y. This vector cuts the parallelogram into two identical triangles. As you may already know, in every triangle the length of one side is always lower than the sum of the lengths of the other two sides. However, the rule says lower or equal. This is because x, y or both of them might be equal to 0. In that case the absolute value of x plus y is equal to the absolute value of x plus the absolute value of y. Let's calculate the subtraction of two complex numbers now. As we did before, we consider two complex numbers x and y, expressed as a plus bi and c plus di respectively. But the number z corresponds to the subtraction of x and y. We can apply again the summation of all the terms of x and y, remembering that the terms of y are multiplied by -1. So, we will end up with a number which has a real part equal to a minus c, and an imaginary part equal to b minus d. We can think of subtraction as the addition of the negation of a complex number to another complex number. Negating a complex number simply means to multiply that number by -1, which corresponds graphically to applying a central symmetry transformation of a complex number with respect to the origin, as you see in the figure on the left. Once you have determined the negation of a complex number, you can apply again the parallelogram rule with one complex number and the negation of another, as you see in the figure on the right. In this section we will see how to calculate the multiplication of two complex numbers in their algebraic form. Let us consider again the complex numbers x and y, expressed as a plus bi and c plus di. We will then calculate z, corresponding to x times y. To calculate z, we multiply all the terms of x and y, as we would do with the multiplication of two binomials. In this case, you have to remember that the imaginary unit, I, is the square root of -1. So I squared is -1. Then, you should end up with a number which has a real part equal to AC minus BD, and an imaginary part equal to AD plus BC. There is another kind of multiplication you can do with complex numbers, and it's the multiplication of a complex number with a real number. Here we can call our real number k, and the complex number you will end up with is Ka plus Kbi. There is an important rule you should remember about the absolute value and the multiplication of complex numbers. This rule states that the absolute value of x times y is equal to the absolute value of x times the absolute value of y. Of course, this rule holds also for the multiplication of a complex number with a real number. Let's represent this case graphically. If we multiply x by k, which in this case is 2 in the figure on the right, the resulting vector has the same direction as x, and the modulus equal to the modulus of k, which is 2 times the modulus of x. Finally, let's see what happens when we multiply a complex number by I. If you have a complex number x equal to a plus bi, the number ix will be equal to ai plus bi squared. As I said before, I squared is equal to -1, so ix is equal to minus b plus ai. Let's represent this operation graphically. As you can see in the figure on the right, given a vector x, the vector ix is the vector x rotated by 90 degrees in the counterclockwise direction. If you multiply x by -I instead, the vector -ix is the vector x rotated by 90 degrees in the clockwise direction. In this section we will see how to represent a complex number in its polar form, and which are the advantages we can get from this representation. To start, let's consider a vector in the Cartesian plane, a generic vector r, which forms an angulus theta with the x-axis. Will have coordinates rx and ry equal to the modulus of r times the cosine of theta, and the modulus of r times the sine of theta respectively. Then, we can use the analogy with the complex plane to represent a complex number in its polar form. Let's consider a generic complex number r in its algebraic form, which corresponds to a plus bi. The vector representing r on the complex plane forms an angle theta with the real axis. So, as we did on the Cartesian plane, we can represent rar the absolute value of r times the cosine of theta plus I sine of theta. So the real part of r is absolute value of r times cosine of theta, and its imaginary part is absolute value of r times sine of theta. If the angle theta is unknown, you can calculate it using the ratio of the imaginary part and the real part of r. As you can see from the equations below, that ratio is equal to the tangent of theta. So you can calculate theta as the arctangent of the b over a ratio. The angle that a complex number forms with the real axis is called the argument of that complex number. Now that you know how to represent a complex number in its polar form, you can use it to slightly simplify the expression of the multiplication of two complex numbers. And to see what it means to multiply two complex numbers geometrically, let's consider two complex numbers x and y, expressed as absolute value of x times cosine of alpha plus I sine of alpha, and absolute value of y times cosine of beta plus I sine of beta. We can calculate their product as we did before, when we calculated the multiplication of two complex numbers in their algebraic form. By doing so, we will end up with an expression of xy equal to the absolute value of xy times cosine alpha, cosine beta minus sine alpha sine beta, plus I times cosine alpha sine beta plus sine alpha cosine beta. We can simplify this expression by applying the addition rules we know from trigonometry. So we will end up with the product xy expressed as absolute value of xy times the cosine of alpha, plus beta, plus I times sine of alpha plus beta. We can now represent the multiplication of two complex numbers graphically, considering the expression we obtained before, and the rule of the absolute value of the product of complex numbers. The result of the product of two complex numbers, x and y, will be a complex number with an absolute value equal to the product of the absolute values of x and y, and an argument equal to the sum of the arguments of x and y. The figure on the right represents this result graphically. In this section we will see how to calculate the reciprocal of a complex number. As you may already know, multiplying a number by its reciprocal will give a result equal to 1. The same is true when we multiply a complex number by its reciprocal. We can then apply this rule to obtain the general expression of the reciprocal of a complex number. Let's consider two complex numbers. X as a given complex number, expressed as a plus bi, and y as the reciprocal of x, which is unknown, and is expressed as c plus di. To calculate y, let's set the product xy to be equal to 1. We apply again the algebraic multiplication of the terms of x and y. since the product of x and y is equal to 1, which is a real number. The real part of xy should be equal to 1, and the imaginary part of xy should be equal to 0. So we have to solve the system of linear equations you see in the center of this slide. If you do the math, you should end up with a result like this. C is equal to a over a squared plus b squared, and d is equal to minus b over a squared plus b squared. The reciprocal of x, then, is equal to a over a squared plus b squared, minus b over a squared plus b squared times I. We can now represent the reciprocal of a complex number graphically. As we know from the properties of absolute values, the absolute value of 1 over x is equal to 1 over the absolute value of x. And the argument of 1 over x is equal to minus the argument of x. This is because the argument of 1 over x is equal to the argument of 1 minus the argument of x. And since 1 is a real number, which lies on the real axis, its argument is equal to 0. The figure on the left represents the reciprocal of the complex number x graphically. In this section we will see how to calculate the conjugate of a complex number. The conjugate of a complex number x, indicated as x star, is defined as a complex number which has the same real part of x, and the imaginary part equal to minus the imaginary part of x. So, the absolute value of the conjugate of x is equal to the absolute value of x, and the argument of the conjugate of x is equal to minus the argument of x. The conjugate of a complex number corresponds graphically to applying a symmetry transformation with respect to the real axis to a given complex number. As you can see in the figure on the left, we can now multiply a complex number by its conjugate by applying again the product of the terms of a complex number x, expressed as a plus bi. We will end up with x times x star equal to a squared plus b squared, which is equal to the square of the absolute value of x. In this section we will see how to calculate the division of two complex numbers. We can use our knowledge on the reciprocals and conjugates of complex numbers to calculate the result of the division of a complex number. Let's consider two complex numbers, x and y, expressed as a plus bi, and c plus di. We can think of the division 10 over y as the multiplication of x by the reciprocal of y. The reciprocal of y is equal to c over c squared plus d squared minus d over c squared plus d squared times I. So the fraction x over y is equal to ac plus bd plus bc minus bd times I over c squared plus d squared. If you look at this result, you should notice that the numerator is equal to the product of x and the conjugate of y, and the denominator is equal to the square of the absolute value of y. In this section we will see how to represent a complex number in its exponential form. As you will see later, this is a form which allows us to simplify further the multiplication and division operations of complex numbers. In order to represent a complex number in its exponential form, we have to use the Euler's formula, which related the complex exponential function with trigonometric functions. The formula states that the exponential of I theta is equal to the cosine of theta plus I times the sine of theta. Let's consider a complex number x written in its polar form, which is absolute value of x times cosine of theta plus I sine of theta. We can substitute the trigonometric functions with the Euler's formula and obtain the result: x equals absolute value of x times the exponential of I theta. Now that you know how to represent a complex number in its exponential form, we can use this form to simplify the expression of the multiplication of two complex numbers. Let's take two complex numbers in their exponential form, x equal to absolute value of x times the exponential of I alpha, and y equal to the absolute value of y times the exponential of I beta. The product xy is equal to absolute value of xy times the exponential of I alpha times the exponential of I beta. From the properties of exponentials, we know that the product of two exponentials is equal to an exponential with the same base and the exponent equal to the sum of the exponents of the exponentials multiplied. So, the product xy is equal to absolute value of xy times the exponential of I alpha plus beta. We can apply the same reasoning for the division of two complex numbers. In this case, the fraction x over y is equal to absolute value of x over absolute value of y times the exponential of I alpha over the exponential of I beta, which is equal to the fraction of the absolute values of x and y times the exponential of I alpha minus beta. In this section we will see how to calculate the powers of complex numbers. We can use the properties we have learnt so far to calculate the nth power of a complex number x. Since the absolute value of the product of two complex numbers is equal to the products of their absolute values, we can take the exponent n out of the absolute value operator. And, since we know that the argument of the product of two complex numbers is equal to the sum of their arguments, the argument of x to the power n is equal to n times the argument of x. We can try to visualize the shapes we obtain by calculating the powers of a complex number. As you can see on the left, if we calculate the powers of a number with absolute value greater than 1, the absolute value of that number will progressively increase. The resulting shape is a sort of spiral which enlarges as the exponents increase. On the contrary, as you can see on the right, if we calculate the powers of a number with absolute value lower than 1, the absolute value of that number will progressively decrease. The resulting shape is a spiral which shrinks as the exponents increase. In this section we will see how to calculate the roots of complex numbers. Let's consider a number y, which is equal to a number x raised to the power n. Then, x is equal to the nth root of y, or to y raised to the power 1 over n. So, the absolute value of x is the absolute value of y raised to the power 1 over n. You may also think that the argument of x is equal to the argument of y divided by n. But this is only partially true, as this is just one of the n roots of y to the power 1 over n. This is because, if you add 360 degrees, or 2 pi radians, to an angle alpha m times, where m is any integer non-negative number, the sine or cosine of that number won't change. So the argument of x is the argument of y plus 2m pi divided by n. In our case m goes from 0 to n minus 1. Since the argument corresponding to m equal to n will be the same as the argument corresponding to m equal to 0. The same is equal for m equal to n plus 1 and 1. And so on. Let's visualize this operation graphically. Let's say we want to calculate the 6 roots of minus 0.5 to the power of 1/6. The number minus 0.5 is a real negative number, so its roots will be complex numbers. The argument of minus 0.5 is 180 degrees. So the arguments of the roots will be calculated as 180 over 6, which is 30, plus m times 360 over 6, which is m times 60. The first root, then, will have an argument of 30 degrees, which is the one you see in red in this figure. And to calculate the arguments of the remaining roots we will add 60 degrees 5 times to the argument. Congratulations! You have reached the end of this course. If you liked this course and you would like to see more courses like this, Please leave a like and subscribe to my channel. Even though my tone of voice is not very enthusiastic, I can assure you that it would make me really happy. Also, if there are some specific courses you would like to have, feel free to tell me that in the comments. If it's a topic I have enough knowledge about, I will surely upload it someday.